items. And one of it, anything wrong with the machine? So let me stop here. So what's going on there? Is that now? Okay. So let's move on. Okay, so now there are two items here, right? And we have to deal with it. This is from the perspective of I, right? This is from perspective of J. And this one is Ij, right? So this one will be affected by J. So you cannot move this out. But this one is mu I and mu, right? It is not affected by J. It is not affected by J, so we can move this out, okay? So these two items, okay, it is already done there. There's no way to further simplify it. But this one, we can, when we simplify, we will find out this is actually equal to 0, okay? So let us try to deal with this item here. So this one can be written like this. Mu I minus mu I from 1 to R, summation Ni j equals from 1 to Ni, Xij minus mu I, right? Okay. And actually this one is equal to 0, okay? Why this one is equal to 0? Let me show you here, okay? We know, let me see if it is here. No, it's not. Okay, mu I is equal to, as we talked about it last hour, 1 over Ni summation j from 1 to Ni xj, right? But here we are talking about a specific machine I. And now, the same thing we are talking about machine I, right? But because in this case, actually, we are not dealing with I here. So here it is any individual I, right? So basically, this one, okay, will be equal to that one. And so let us say here, let us simplify that part there first, okay? Xij minus mu j, right? This one is equal to summation Xij minus summation mu j, right? And so this is from 1 to Ni, okay? From 1 to Ni. So this is summation Nij from 1 Xij minus Ni mu. That is mu I, I'm sorry, that is mu I, right? That is mu I. Okay? So then here. So if you look at this formula, and if you look at these parts, basically they are the same thing, right? This one is equal to that one, okay? So this part is actually equal to 0, right? So, do I go too fast? Okay, basically from here you know this one can be derived, can be simplified to this one, right? And so when you compare this one and this one, you know that the whole thing should be equal to 0, right? And so because of that, then we can put down the formula like this. Summation Xij minus mu square is equal to summation Xij minus mu I square plus summation mu I minus mu square. Okay? So then you know that this one is SST equals SSE plus SSF. Okay? This is what we call sum of square total. This one is sum of square error. This is sum of square factor. Okay? So then, what's going on here? So basically, whatever deviation of the total deviation, okay, from each individual item to the whole population, it is here, okay? It has two components. The first part is due to error. The second part is due to factor, okay? Then, H naught is mu1, mu2, and equals to mu r, and H1 is H naught is not true, right? So if indeed, okay, H naught is true, if indeed H naught is true, okay, this part should be equal to 0. This part, or in other words, this part should be equal to 0, right? Because that means each machine actually produce the same quality, okay? The products are of the same quality from the machines. If that is the case, mu I should be equal to mu, right? So that would be 0, okay? That would be 0. So if H naught is true, then we know SSF should be equal to 0, okay? But as you may know, we won't be able to check every item of the population. We won't be able to do that. The only thing we can do is to get samples out of it, right? So we get some samples out of the population, and from the sample we want to infer what's going on in terms of the population. So from this perspective, we know, because we do it by sampling, and there is sampling error, right? There is sampling error. So we won't be able to know whether this is going to be true or not, because on the one hand, we do it by sample and there's sampling error. On the other hand, the machine may not be equal to each other, okay? I mean, the quality produced by the machines may not be equal to each other. So we have to use some other statistics, okay? We have to use some other variables, estimators, try to deal with this situation. But before we go over that, okay, we will show you again the whole thing, but in terms of the formula from sample, okay? We have to use sample. So we know SST is equal to SSE plus SSF, right? But here, it is the formula written in the form of population, and now we want to put down the formula for samples. Okay, so it will be summation, the same thing, xij minus x bar g. Okay, x bar g. That means the sample mean for the whole sample, okay, for everything included, okay, for everything included. And then the second part is the square of total, square of sum due to error. It is summation xij minus x bar I squared. Okay? And then the third part is x bar I minus x bar g squared. Okay? So this is the formula in terms of sample, and this is the formula in terms of population. So we have different notations here. You want to be careful. But basically, you have to tell yourself, okay, this formula, to be sure, is a little bit complicated, but it is kind of easy to remember. The first one is the total deviation, right? The total deviation, individual item with the whole population mean, okay? Individual item and the whole population mean. The second one is due to error. So if it is due to error, then we are looking within each machine, okay? So I, x bar I, right? And of course, j from 1 to ni. The same thing here. This one, we are looking at the factors. So if the machines are different with each other or not. So we are looking at across machine. So x bar I to x bar R, okay? So basically, this is the formula for this, okay? You want to try to get yourself familiar with all this. And then we want to say something about ANOVA. So when we do ANOVA analysis, okay, basically we have three assumptions. And in this case, we only talk about one factor, okay? The books talk about 2 factors, 3 factors, but in this class, we only talk about 1 factor. And, sorry, I got something wrong here. ANOVA, right? There are 3 assumptions. The first one is the small population must be normal. Basically, for whatever xi you have, it is a normal distribution. Okay, whatever machine you are talking about, it is a normal distribution. The second one is homogeneous. Homogeneous variance. Homogeneous means the same. So what does this say? This say sigma 1 square is equal to sigma 2 square is equal to sigma r square, and that is equal to sigma square. Okay? So basically, for the machines, right, we assume they have the same variance. Okay? The machines have the same variance. The third one is fixed effect. Fixed effect. So we say, you know, for the machines, the effect is fixed. Okay? We don't talk about anything other than this. For this one, it's a little bit complicated to explain it, so let us forget about it. But basically, these 2 conditions are very simple. Okay? You want to make sure that they are equal to each other. Okay? Because we already talked about F distribution, right? We have discussed F distribution before. So if I want to make a more complicated final, okay, if I want to make a more complicated final exam, I will tell you to test whether the questions, okay, the variables we talk about in the questions have the same variance or not. If the variance are the same, then you can use ANOVA. If the variants are not the same, you cannot use ANOVA. Okay, you want to remember this. If I want to make a question more complicated, I won't tell you which method to use, okay? I will tell you to test first whether the variances are the same or not. If they are the same, then you can use ANOVA. If they are not the same, can you use it? No, okay? Okay, let us move on. Okay, now we want to get to MST, MSE, and MSF. We already mentioned this because if H naught is true, right? Then SST equals SSE, okay? We already mentioned this. But somehow if you look at, so that means SSF is equal to 0. But somehow if you use this, okay, it is kind of complicated to deal with it because these are all numbers, right? And we know the more machines you have, with more machines, of course, all these numbers will increase, right? So from there, you won't be able to tell what's going on. So we have to consider what's going on in terms of machine, right? So we want to make sure that the deviation due to each machine, okay, is small. If that is the case, we say that is more a sensible way to test this hypothesis. So then we want to talk about average. Average is mean, right? So MST is equal to what? SST divided by the degrees of freedom there, okay? So what is the degrees of freedom in terms of SST or MST? Because in this case, you are talking about this one, right? MST is SST divided by something, and we want to know what should be this number here. So in this case, right, how many samples do you have? You have our machine, okay, here. And J is 1, 2, and R, okay? Because we are talking about samples, so we use little n. We use little n. And so here, the total number you have, okay? And this is a value you know. This is x bar g, right? So in this case, if you know n minus 1 of it, but of course we are talking about the samples. So actually the total for them is n. But because you know a sample mean, right? You know the grand sample mean, the sample mean for the whole samples. So the degrees of freedom is actually n minus 1. Just the same thing, we say x1 and you have xn, right? And if you know x bar, what is these degrees of freedom? n minus 1, right? So basically this is the same thing. But you want to make sure you know what's n here. So the n summation I from 1 to R. Okay, so n I equals n. And that is n1 plus n2 plus nr. Okay, so this is the total number we have. We talk about the case for population, right? Population is cap n, and n1, n2, nr. Okay, and that is the whole thing equals big N. Okay. So in this case, if we want to get a mean square total, it should be this one, right? The degrees of freedom is the whole thing minus 1. And now we are talking about this one, MSE, right? MSE, the same thing, should be equal to SSE and minus something, right? Okay, so SSE is here. Here we are also talking about individual items. The relationship between individual items and all the machines, okay? How many machines do we have? we have R machines, right? If we have R machines, so we have how many sample mean? X bar 1, X bar 2, and X bar R, right? So in this case, we have only one sample mean, so we have M minus 1. And we have R sample mean, so it should be M minus R. So that is summation Ni minus R, okay? The third case, it is the mean square due to factor. You want to remember this. The starting point, the basis for this is for all the individual items. And the basis for this is also individual items. But in this one, we are looking across the machines. We are looking across the machines, so how many machines do we have? We have R machines. We have X bar 1, X bar 2, to X bar R, right? And from here, we also know there is one thing we know, that's the mean for the whole sample, right? So in this case, how many degrees of freedom do we have? Because these are treated as variables. And this one, we know that. So it is R minus 1, okay? So MSF will be equal to SSF divided by R minus 1, okay? So basically, this is what we have. After we get sum of square total equal to sum of square error plus sum of square due to factors, then we want to get to the MST, MSE, and MSF. Again, just want to remind you something you need to be careful. So we have SST equals SSE plus SSF, right? We know this one is equal to the sum of the other two. But what about here? MST. Will this one be equal to the other two? The answer is very clear, right? It should be no. Because it is not divided by the same number, right? So this one, MST, is divided by this number, right? And this one is divided by this number. And that one is divided by this number. If they have to, if this equation gonna hold, it has to be divided by the same number, right? But it's divided by different numbers. So it is not equal to that. MST is not equal to MSE plus MSF, okay? Okay. Any questions? Let us continue to talk about the properties of this distribution, because the first thing is we want to know what kind of statistics to use. Okay? After we get the statistics, then we need to know what kind of distribution, right? What kind of distribution we should use. So let's move on. Okay, we want to deal with it from population, okay? So we have summation I is equal to n, right? And now we want to deal with the individual variance. So sigma I squared should be equal to 1 over ni summation xi minus x, this should be mu. Okay, so the same thing, this is from the the angle of population. If we want to deal with sample, then it should be xi squared, right? And then 1 over ni, summation j from 1 to ni, xij minus, then it should be x bar I, right? Sorry, I make a mistake here. It should be, what should be here? It should be ni minus 1, right? Ni minus 1. Okay. Any more questions? So then we have these two things, right? But let us say we want to talk about the variance for the whole population. Okay, the variance for the whole population. What should this be? It should be equal to 1 over n, and then summation xij minus mu squared, right? So basically this will be the same thing as we have done from SST, right? Remember, what is this? This is actually SST, okay, this part. This part is actually SST, right? This part is actually SST. But anyway, let us move on. We have 1 over n, summation xij minus mu I plus mu I minus mu square, okay? The same thing again, summation. Here you have xij minus mu I square plus mu I minus mu square plus 2 times xij minus mu I and mu I minus mu. Okay? Any questions? So we're gonna simplify it again and try to figure out. Okay. The same thing, right? This part will be equal to 0. So this part is equal to 0. So what do we have? Equals 1 over n summation xij minus mu I square, okay, plus 1 over n summation mu I minus mu square. Okay, so you can actually get something familiar from here and there, okay? So if you look at this, actually it's the same, right? If you look at only this part, of course this is from I1 to R, J from 1 to Ni, excuse me. So if you compare this part, okay, this part, J from 1 to Ni, this part is the same as this one, right? Okay? But what's going on here? There is 1 over Ni. So as a matter of fact, this one, okay, can I erase this one? Let me erase this part, okay? So what can you get? You get Ni times sigma I squared, actually equal to summation xij minus mu I squared, and j is from 1 to Ni, right? Okay? So this part is actually equal to this part. So what can we do? We can say this one's 1 over n summation I from 1 to R times Ni sigma I squared, right? Okay, because this part is equal to this part, and this part is the same as that part, okay? And then here you have 1 over n summation, of course this I to r, I from 1 to r, j from 1 to ni, okay? Because here is mu I minus mu, right? Mu I minus mu. Is it affected by j? No, it does not affect, it's not affected by j. So actually we can get, this is from 1 to ni, right? So I from 1 to r, ni times mu I minus mu squared. Okay? Any questions so far? And as you may remember, we say when we discuss ANOVA, we have 3 assumptions, right? One of it is the population must be normally distributed, and the second one is the variance should be the same, right? So sigma 1 square equal to sigma 2 square equals sigma r square, right? Okay, so in this case, this one is actually equal to 1 over n summation r ni times sigma square, because for all the variance they are the same, right? They are the same. And then here 1 over n summation ni mu I minus mu square I from 1 to r. Okay? Okay, and because this is a constant, so you can move this out, right? So it becomes sigma square times sigma n summation ni n plus n 1 over n and ni mu I minus mu square. And what is this equal to? It is here, right? Summation ni is equal to n, right? So it is equal to 1. Sigma square plus 1 over n summation ni mu I minus mu square. Okay? So finally we find out what's going on here. Okay? If, let me erase this part. If H naught is true, then sigma g square must be equal to sigma square. Okay? So if it is true, if H naught is true, that means this part will be equal to 0, right? If H naught is true, then this part is 0. Then sigma g square, so that's the population mean. Okay, the population mean must be equal to, the population variance must be equal to the variance of each individual machine. If this is true, then this should be true. So that's the reason we have, we call this ANOVA, right? Basically, we are testing, okay? Basically, we are testing whether the mean of each machine is equal to each other or not. That's what we are testing. But finally, we will figure out if the mean are equal to each other for, the mean for the individual machines, if they are equal to each other, then we realize if that is the case, then the population variance should be equal to the variance of each individual machine. Okay? Okay, then the second part, okay? What is the second part? If H1 is true, then what do you know? If H1 is true, then sigma g square must be greater than sigma square. Okay? Because if these two things are not equal to each other, right? And this is square, so it must be positive, right? It must be positive. So if H naught is true, then sigma g squared must be equal to sigma squared. But if h1 is true, then sigma g squared must be greater than sigma squared because of the terms here. Okay? Any more questions? I think we will defer some of the discussions to next week. Let us stop here. 我看你们一堆人都要睡着了。What kind of decision you will make? Because this one is still larger than this one, right? So still we accept H1, reject H0, okay? So we get back to the question here, okay? So this is a larger sample size, so we use normal distribution. So let us look at the next example, okay? The next example is an insurance company, okay? This insurance company reports that the mean cost to process a claim is $60, okay? So we know the mean cost is equal to $60, okay? And industry comparisons show that this amount to be larger than most other companies, okay? So they instituted cost-cutting measures. Okay, so the original cost for them is $60, right? It is $60, but somehow they find out that this cost is too high. Of course, when you find out that the cost is too high, what should you do? You need to cut costs, right? When you figure out the cost is too high, of course you will take actions to cut your cost. And then, after cutting the cost, after you take actions, of course you want to try to figure out whether you have reduced the cost or not, right? So in this case, what should be your alternative hypothesis? You want to figure out whether the actions are effective or not, okay? Whether the action can indeed reduce the cost. So the alternative hypothesis should be 60, right? I mean less than 60, because you will try to figure out whether you have done something effective or not, right? And then the null hypothesis is that, well, still the same thing, right? You haven't done anything. I mean, you have done something, but the actions are not effective, okay? Okay, so let us continue. So they institute cost-cutting measures. To evaluate the effect of the cost-cutting measures, McFarland selected a random sample of 26 recent claims. Okay? What does that mean? They take 26 claims. So they take 26 sample. The sample size is equal to 26. So what kind of distribution should you use? Z or T? T distribution, right? Degrees of freedom? Degrees of freedom? 25, right? Degrees of freedom, 25. Okay. And so now they find out that the mean cost is 57. Okay, the mean cost, that's X bar, right? They do a sample, I mean, they calculate the mean from the sample, they get 57, and the SX, the standard deviation, is equal to 10. And we want to use a significant level, okay, alpha is equal to 0.01, okay? So basically we can throw all this information into a diagram, okay? So you want to make sure you are able to do this. If you are not able to do this, you're going to get into trouble. That's what I'm going to promise you, okay? You want to be able to draw all these things, and then because the question will further ask you about beta, okay? Okay, let us try. So we have we are comparing this, right? 60. Okay, 60 is here. And we know, we want to make sure that indeed the actions are effective. It can indeed cut the cost. Okay? So this is a left tail test. Okay? We want to make sure that indeed the cost is cut. And so we need to figure out what's the critical value here. Okay, what's the critical value here? And so then, because now it is T distribution, right? It is T distribution, so you need to figure out, okay, this will be 60, okay? Because basically, when in this case, you are still assuming, okay, H naught is true, right? Under these circumstances. And so you need to figure out this one, and it should be, let me give you the formula first. It should be X bar naught minus, right? In this case, it's minus. T, the greatest of freedom is n minus 1. And in this case, the significant level is 0.01. So it should be 0.005, right? Times Sx squared divided by n, okay? Divided by n. The degrees of freedom is n minus 1. But this number is n. Okay, this number is n. So this is 60, right? Minus. Can anyone tell me what's this number? It should be in the book, right? What's this number? You want to be able to check the table, right? And this one will be Sx squared. That will be 100, right? 100 divided by 26. What's this number here? Does it say that here? Okay. The book shows you how to check the table, right? Look at page 353. Okay, page 353. So that's 2.4855, right? 2.485. Can anyone tell me what's this number? Get a calculator. So it's 60 minus 2.485 times, should be close to 4. Close to 1.865. 96, okay, thank you. Okay, then what's the total number there? $4.86? Okay, good. A7. Okay, so then you've got, it is 55.13, right? So the critical value here should be equal to 55.13. Okay, so then, because the value you get is 57, this is the value you get. But this is the critical value there. So 57 is somewhere around here, right? So what would you do? You're going to accept H naught or reject H naught. You're going to accept H naught because it's above this critical value, right? So what does that mean? That means the company has not done enough to cut the cost. They should take more actions to cut the cost because their cost is still high. Okay? Because if they indeed cut the cost, the value should be below this number. Okay. Okay. And now let us assume. Okay. Let us assume. Because the next step, I want to tell you how to calculate beta. Okay. The next step, I want to tell you how to calculate beta. So let us say indeed the H1, okay, the mu x is equal to 57, right? So let us say indeed you figure out the new cost is actually 57. So in this case, how to calculate beta? Okay, how to calculate beta? So we know in this area it is 1 minus alpha, right? And this area is alpha, right? And now, hold on. So, can you still get a sound there? Anyway, when did it happen? No idea. Okay, let's move on. We want to calculate the beta there. Okay, so we know this is 55.13. Okay, and now we say H1, the mu is actually 57, right? So this is 57. If the value is below this, you take A1, right? If the value is above this, you take A0, okay? So in this case, what is this value and beyond if H1 is true? If H1 is true, this one should be 1 minus beta, right? And this one should be beta, okay? And so how to calculate beta? In this case, beta will be equal to probability of x bar, okay? That is greater than or equal to 55.13, okay? So basically, you calculate, you get a z, right? And calculate, you got this area and then plus. So that is P, okay? X bar between 57 and 55.13, but this area only covers this area, right? And plus 0.5, right? So that's beta. So in this case, you know alpha is very small, right? In this case, alpha is only, where is it? Alpha is only equal to 1%, right? What happened to beta? How much is it? It is at least 50%. So the type 2 error is actually very high. Okay, the probability of type 2 error is actually very high. So sometimes you just look at this number, but you have to look at this number too, right? I mean, this number is going to show you that even though the type 1 error is very small, but type 2 error is very big. Oh, there's a great risk there, okay? What time is it now? We have some more time, so let us move on. Let us get to question 3, the question on 355, page 355. Okay, the same thing here. The mean length of a small counterbalance bar is 43 millimeter, okay? And then the mean, where is the mean? The mean is 43, right? So mu x is equal to 43. And how many bars do you get? You get a random sample of 12 bars, okay? You have 12 bars. So that means the sample size is equal to 12, right? And okay, so in this case, you have to calculate here. So let us get rid of this. So for this question, it is a little bit tedious. You have to calculate x bar 0 yourself, okay? You have to calculate it. And then also you have to calculate Sx yourself, the sample mean and sample standard deviation. And the alpha, okay, the significance level is equal to 0.02, okay? So you should be able to figure that out. And because there are only 12 samples, right? Only 12 samples. So what is the degrees of freedom? The degrees of freedom is equal to 11, right? Degrees of freedom. And let us see what's going on here. So at line 3, okay, at line 3, he asked the engineering department to investigate. What's our concern? The concern is that the production supervisor is concerned that the adjustment of the machine producing the bars have changed. Okay? So the same thing, right? We are concerned it has changed. So if it has changed, that means it is not equal to, right? So we are concerned whether it is equal to the original size or not. Okay, so that's our concern. So in this case, our concern is whether it is equal to or not, whether it has changed or not. So equal to or not equal to, right? Equal to or not equal to, and the number should be 43 here. So basically, you just follow the same rule, okay? You follow the same rule, you should be able to get the answer, okay? So let us stop here and we will continue next week. Thank you.